This conference will now be recorded.
Okay. So for today's class, guys, I think we've already discussed the agenda in our last week's session, right? So we're going to be discussing two topics, to kind of save time. We're going to be discussing two topics today. One is NLP, natural language processing, and then another one is Spark. So we're not kind of, I would say, compensating on anything. Compensating is not the right word. I would rather say we're not leaving out any of these stuffs in both the topics. So what we're going to be doing is we are kind of combining them. That is, we'll try to be making use of Spark. Okay, so one is we have spoken about NLP. The second one is Spark, right? So we will be trying to use Spark as our processing engine, and we will try to do NLP on top of it. Okay. So in the last class we did discuss about the agenda, right? So we spoke that we'll be talking about NLP, natural language processing, and Spark today. So we're kind of combine, kind of bringing both the things together, where we'll see a lot of examples of NLP on top of Spark programming here. That is, how do you use Python and the Spark processing engine to do, let's say, all your, NLP related stuffs here. Okay. So what we can probably do is, guys, we can first jump into, what I would say is the benefits of using Spark. What do you exactly mean by Spark? So that's exactly what I think will be the right thing to do, the right thing or the right area to probably start off with. Okay. So just give me a second. I'll just quickly open OneNote. Then I think we can start a discussion about Spark. Okay, so here we are. So as I told you all guys, so for today's session, we're going to be discussing Spark and NLP, where we'll be using your Spark as a processing engine, and we'll try to do a lot of NLP examples on top of it, right? So the very first question is, what exactly do you mean by Spark, right? So why do you think is this guy qualifying under big data? What are the benefits of using somebody called a Spark? Or what exactly is the difference between the previous topics like Hadoop that we've discussed versus the Spark that we're going to be discussing today? So the Spark, guys, is actually speaking, as most of you might have heard, right? It's more of a processing engine. Okay. So to kind of keep it simple, what previously happened was, previously when we were using Hadoop, right? So you typically called this as, a distributed computing system, right? So what do you call that as? You call it as DSM, in fact. So DSM is more like, distributed processing or distributed shared memory. You can call it as anything. So DSM previously we used to call this as what? Distributed processing or distributed shared memory, right? So whenever we were using Hadoop, what actually happened is that whenever we try to do certain processes, right? So let's say, for an example, you go back and write, let's say, an NLTK code. What will happen is your data would be sitting in your HDFS, as all of us might know, right? We have been playing with HDFS since last week. And your iteration number one, or let's say I'll call it as my job number one, will start working on this particular data that will fetch the data from HDFS. So there'll be a lot of interim data that they will have to store, right? So say for an example, you ask them to create a linear regression model. He needs to store what is the error value. He needs to store what are the coefficients, right? Or what exactly is the prediction that the model is coming up with right now? What is the R square of your predictive model? So all those interim results, when he wants to store, if you look at Hadoop, right? Hadoop is actually going to go back and store it inside your HDFS itself. That is, it's basically a hard disk where he's trying to store the data. Similarly, if there is another job, right? Let's say job number two, he is also going to do some work, and the result of his iteration is also going to get saved in the HDFS here. So what exactly is happening? So the reuse of data, or let's say the sharing of the data, while you're doing this distributed computing, like let's say the MapReduce programs that you see in Hadoop, they are basically storing it in HDFS, or let's say if you're working in cloud systems, it can probably be your Amazon S3 buckets, etc. So the problem is that, guys, since the IO operations, that is the input and output operations, are actually happening on HDFS, right? The overall computation speeds of all of these people is going to be very, very slow. What will happen? The overall computation of all of these jobs, right? Because there's a lot of IO operations, there are certain replications that's happening. That's also a very, very important point. There is IO operations happening. There are replications that are happening because he has to make copies of the data. Then, serialization, deserialization, more like how does he, send it across in the internet in bandwidth. Say, for an example, if I'm running my job here from India, right, the data has to go to some servers in Canada, some of them in US, some of them, let's say, in UK. So serializing and deserializing, that is passing them over the bandwidth that we have, the internet we have. There are a lot of different factors which will affect the computation time and which will actually bring your time to be what? Higher, or let's say it's going to make it much very, very slower. So the problem is that, guys, whenever you're using a MapReduce program, right, the jobs that you're going to do, they're going to save it in the HDFS, which is actually what? Not so fast, we know it. So there are a lot of IO operations. He's going to do replications, that is, he's going to make copies of the data, then serialization and deserialization while transferring the data over the network. All of these people are going to make your Hadoop systems very, very slow. Or let's say more specifically speaking, there's something called as a MapReduce program, where there's a mapper and a reducer, where the mapper will take care of doing the work and reducer will take care of aggregating the results. The mapper and the reducers are going to take up a lot of time to work on this data because of all of these reasons. So now what do we have? So we have this, guys, okay, so I think University of California or somebody, I'm not very sure which university exactly. So these guys, they started working on a particular processing engine, something called Spark. Okay, I think the group name is called AMP Labs. Okay, they're called as AMP Labs, Automation, Machine Learning, Process something. So they called as AMP Labs. They're part of a particular big university in US. So these guys started working on a specific project saying that, hey, I think Hadoop is good, but it's not too good. I do think that we need to make some kind of improvements on top of this Hadoop. We can still come up with a better processing engine. That's when they started working on Spark, where Spark once again is going to work on top of JVM, that is your Java processes, okay? But actually Spark was built on top of another language, something called Scala. It was completely developed on another new generation language, something called as Scala. So these guys, the university guys, they started working on this particular project, and later on it went on to your Apache Foundation. That is exactly when they started calling this as Apache Spark. Okay, so many of your softwares you would have come across, right? Today we have Apache Hadoop, Apache Spark, Apache Storm, Apache, let's say NiFi, or let's say Apache Flink. Everything is coming under the Apache Foundation, more of an open source foundation. Okay, so even you can probably work on some kind of a software and go back and get some Apache licenses, or like an open source license, but comes at a particular limitations. Some people are not supposed to use it professionally, etc., etc. Not supposed to sell it to people. So those kinds of limitations are going to come. So these guys started working on something called as a Spark engine, which will help you solve all of these problems that the Hadoop is facing using a beautiful process that they came across, which I've already told you, namely something called a Spark. So what exactly is the Spark actually doing compared to what the Hadoop is not able to do, which makes it much more better to the plain Hadoop? So the answer is, guys, Spark once again is not completely independent. Okay, so Spark still needs Hadoop at the back end. Okay, so what does Spark require? Spark does still need Hadoop at the back end. He's going to work on top of Hadoop only. So whenever it is a Spark, guys, the first few problems that we had is what? Number one is a lot of IO operations. That is not the problem, but IO operations on what? On HDFS is the problem. Number two that we had was basically replications. That's another problem. And number three we had was basically what? Serialization, deserialization, right? So they were deserializing and serializing it. So these are the three major problems that Hadoop has faced, right? So these guys, the Spark people, they said, okay, while you're fetching the data from the HDFS, I'm okay. So you can, read it from the HDFS, it's fine. Let your job number one work on top of this particular data coming from HDFS. And the result of this particular computation, instead of saving it back into HDFS, guys, these guys are going to probably store it in your RAM of the system. What are they doing? They're going to save it in the RAM of your system right now. It's basically the RAM or the memory of your system and not the HDFS or the hard disk of your system. Similarly, there can be another job who might work on top of this guy. He is also going to store these data sets that he's going to come across in the RAM. And finally, your last computation, you can just go back and save it in your HDFS. So the point number one, where you have to do repeated IO operations on top of HDFS is kind of solved right now. Why? Because HDFS, right, it's not so fast, right? RAM stands for what? Random access memory. Basically, that's one of the most fastest memory that we have. But the problem is it cannot be long term. You can't save your data in the RAM for a long term because the moment the system is switched off, that's it. The data in the RAM is going to go away. But on the opposite, in hard disk, it's a little different. So we are saying that Spark is more of a in-memory technology, while the other people were not. What is Spark? Spark is saying that, hey, I'm more of an in-memory technology, which means I'm going to store all the data sets inside the memory, that is inside the hard disk right now, and not on the HDFS. Sorry, inside the RAM right now and not on the HDFS like how Hadoop was doing. That's a major change what a Spark is actually doing compared to what a Hadoop was actually doing. Or instead of calling it as Hadoop, the right word would be something called MapReduce. What exactly the MapReduce was doing. That is point number one. So point number two is, in your Hadoop, you started making copies of the data, right? I mean, you're making copies of the data, distributing it across in the different servers. So the problem is that you had to make copies of this particular data, right? That is actually a pretty big problem. One is that I need a lot of hard disk one, then a lot of other extra processes where he has to go for the duplications, etc. That's also big problem. So now what happened is, in Spark, these guys came up with a beautiful technology, something called as RDD. So what do we have? We have a beautiful technology, guys, here in Spark. The technology is basically something called RDD compared to what? The previous DSM. So DSM is what? Distributed shared memory. That is, the memory was distributed and it was also shared. And the data was also getting replicated, right? It's called DSM, distributed shared memory. While RDD is what? Resilient distributed data sets. It stands for what? Resilient, point number one. Distributed is point number two. And data sets is point number three. So RDD is exactly what? Spark's RDD. RDD is basically resilient distributed data sets here. It's called as what? It's called as resilient distributed data sets. So what is so beautiful with this RDDs compared to the old DSM we had? So what exactly does the RDD really do? How does he solve this problem of not replicating your data here? So the first point, guys, we call this as resilient, right? The question is, why do you call this particular technology as an RDD technology, resilient distributed data set? Why is this data set called resilient distributed? It's called resilient. The reason because It is fault tolerant. It is what? It is basically fault tolerant. What exactly do you mean by fault tolerant? So the RDD is actually saying, compared to the Hadoop, right? Let us probably not make, what I would say is duplication of the data. So if I understand correctly, he's not duplicating, right? Okay. So what happens is the RDD is saying, let's not probably go back and duplicate the data and all like what the Hadoop is probably doing. Rather, we can maintain something called as DAG. Okay. So RDD is saying what? He's saying that we can probably keep something called as DAG. It's called as directed acyclic graph. Okay, so we call this as what is called as a lineage graph. So what is the Spark doing, guys? The Spark is saying that, hey, compared to what your Hadoop was doing, where he went on to save the data in the hard disk and he went on to make copies of the data, I don't have to do all those things. I have a beautiful technology that I've come up with, which is basically RDD, which stands for Resilient Distributed Data Sets. So why would you call it as resilient here? Because we think that it's fault tolerant. Not like think, of course, yes, it is fault tolerant. What do you mean by fault tolerant? I mean, it's okay for him to have some certain faults and all. He's okay, he's ready to tolerate it because he has certain technologies to solve those problems. What is the technology, guys? We have something called DAG. It's called directed acyclic graph. It's basically a lineage graph, okay? What do you mean by a lineage graph? So he knows that, okay, I had a big data set, right? My user had probably given me a big data set. So say for an example, he gave me a 1 GB data set here. What I will do is I will go on and divide this data set into small RDDs. I'll create what is called as partitions. So I have one small piece of the data, another small piece of the data, another small piece, another small piece of the data, another small piece here. So this would probably become RDD1, this will become RDD2, 3, 4, and 5. Now what might happen is, guys, so this could have been a bunch of people, okay? So what you're doing is you're probably writing a group by function. So you're saying, hey, a group by the name of the people and tell me what is the sum of their salaries. So this is exactly what you're doing. So what are the operations you're doing? First thing is you're doing a group by operation. So what happens is he'll create a new RDD called a group by RDD. So he'll basically create a new data set, which is a grouped data set here. So you call this as what? You call this as a grouped RDD probably. Then what will happen is on top of this grouped RDD, you're applying an aggregation. So this might probably become, let's say, an aggregated RDD. I mean, I'm not very sure about this name, guys. I'm just giving you, okay? But there are certain names for those RDDs. So you do one operation, it becomes, let's say, a grouped RDD. You probably do another operation, let's say it becomes an aggregated RDD. Then finally, this is your data set. This is your final RDD that you have. Similarly, same process for this RDD also, same process for this one, same process for this one, same for this one. Then you combine the result, right? So this is exactly what is going to happen within Spark. But the most important point is, guys, while he's dividing the RDDs and he's doing certain transformations, right? So what is he doing? He's doing certain transformations on top of this one, correct? While doing these transformations, he's going to maintain something called as a lineage graph. So what is this guy actually doing? He's maintaining something called as a lineage graph right now, or what we call as your DAG. Okay, the DAG, right? The directed acyclic graph. So he's going to basically keep up what is called as a graph of what has happened. What are exactly the different things that the RDD is going through. He has a complete graph or a complete flow of what is happening on the back end. That is exactly what is called as a lineage graph here. So he's saying, hey, I got a RDD, okay? First, I did a filtering operation. I got another one. I got another map operation, then a third RDD. I did probably a group by operation. I got a different RDD. So all of this process, right? The map of what he is supposed to do, what he has done, everything is typically stored over this particular graph called as a lineage graph. Now, suppose in case, guys, in the previous case, what happened? Your Hadoop, he said, hey, while I create this data sets, right, what I will do is I'll also make copies of it, right? So Hadoop said, I'll always make copies of it. So that suppose in case something goes wrong here, right, the copy of that will be saved in some other server. That server will go on to compute step number 4, correct? That is what Hadoop said, right? So he said, okay, the second RDD you have created, I'll make copies of it. Third RDDs I'll create, I'll make copies of it. But suppose in case the server has got shut down, this server has got shut down. What will Hadoop do? He'll say, hey, I already have a copy, okay? You can continue from there. From that guy, you can continue. That's exactly what Hadoop would have said, right? But Spark is saying, hey, instead of saving it in your hard disk and then calling back and then going back and doing it, right? What we feel is like, you can save it in the RAM itself, okay? So don't make copies and all the RDDs that you're coming up with, let us save it in the RAM. That is point number 1, because it's going to increase your speed right now. Okay, that's a beautiful thing. The second one these guys said is, hey, if something goes wrong here, let's say if the third RDD has got deleted, I have the lineage graph as what has happened, right? I know the flow of things, what has happened, how it has happened, etc. Correct? So what I can probably do is, since I'm working on the RAM only, where I'm very, very quick in processing, I will just go back and start the process over again from the start. So what is he saying? He's saying, since I keep what is called as a lineage graph right now, right? He's saying what? Since I keep a copy of what are the different transformations and the actions that this particular graph is, this particular RDD is going through, if there is anything that's going to happen, say for an example, a loss of the partition or the loss of the data, I don't have to worry because I have the record of what has already happened. I have the record of all the different transformations that he has gone through. So I can just go back and do what? Start over the process again, which will probably do what? Save a lot of time rather than fetching the data from a different server altogether, right? Or probably making a lot of copies. All of these things are beaten by just keeping a track record of what has already happened, what are the different transformations my boss is asked to do. So I keep a track record of all of this lineage. Now this is exactly what I'll go back and just recompute, which will save a lot of time for me here, right? So it's saying what? So we can just go back and replay all the transformations on those partitions, right? To achieve the same output, whatever we want, instead of probably going back and finding out the duplicates we would have created in the multiple nodes, right? So I don't have to waste my time in making copies of the data. I don't have to waste my time in saving things in hard disk. I can compensate for all those problems by just doing it on RAM and by keeping a copy of all the different operations that this guy is doing. So this is exactly what is different in RDD compared to what? Compared to the Hadoop that was actually doing the same previous job here, right? So this is the beautiful point, guys. So the RDD is a beautiful technology that these guys have come with. Resilient distributed data sets. Why do we call it as resilient? Because it's fault tolerant. Because even if there is going to go, even if there's something that's going to go wrong, right? If there's something faulty, you don't have to worry because I'm tolerant to all these problems because I keep a track record of all the computations I have to do, and I can just go back and do the same thing again. Rather than replicating the data set, saving it, wasting a lot of time, reading it from hard disk, I don't have to waste my time on that. Rather, I can just go back and do all the processes again. This is exactly what is beautiful with the RDDs. We call it as resilient here. What exactly do we mean by distributed? That is the next question. distributed, I'm pretty sure all of you would have understood, right? So what do you mean by distributed? So you're saying, hey, all the different RDDs, let us pass it to the different nodes, okay? So let one partition go to one of the server. In that RAM, let him work. Another partition, let us send it to a different server. Let him work in that RAM. So the distributed is a case where your data, you're going to pass it to different nodes right now. You're not saving it in a single node. You're passing it on to several nodes. So several workers will be working parallelly in their random access memories. And everybody will keep a track record of what is the lineage, what has happened, what is supposed to happen. They know all the transformations and actions here. And why do we call this as data set? Because ultimately they hold data, right? So we call them as data sets, which can be of any format like JSON, CSV, text file, SQL tables. They can be anything. So by the end of the day, they are basically data sets for us. So this is exactly what is different, guys, from Hadoop versus Spark. The Spark has brought a beautiful technology here, something called as RDDs, which you can create it using different methodologies. You yourself can create your RDD from scratch, or you can, go back and probably work on certain functions which can create your RDDs, right? So there are, in fact, multiple ways to do it, guys. One is like, when you're storing it itself, you can store it as an RDD, right? You can parallelize it as an RDD, or you can leave it to functions which can go back and, convert them as RDDs, right? So similarly, some of the RDDs you can go back and save it in your hard disk if you want. Some of them you can keep it in the RAM itself. So all of these partitions, you can play with them as how you like. So the major difference is this, guys. So IO operations no more in HDFS, and replications is not required anymore. Since these two problems are solved, Spark became a massive hit compared to the conventional MapReduce programs that people were writing. So the MapReduce programs, right, they had to go back and save the data sets, etc. So there were a lot of problems, which actually the Spark is actually solving by following this concept of something called as RDD here. Okay. So what a RDD will, what a Spark will actually do is, guys, he'll maintain something called as a Spark context. So what is he going to do? He's going to maintain something called as a Spark context. So Spark context is more of a process, okay? So Spark context is more of a process. So this guy will basically maintain all the workers. So you might have different servers that you would have connected, right? So he will maintain the different workers, and he'll pass the different partitions of data to the workers. He'll ask them to do their jobs, and he'll start aggregating the data here. Okay. So this is exactly what a Spark is actually doing, guys, compared to a Hadoop. This is exactly what makes a Spark system far better compared to a Hadoop. In fact, in some of the cases, right, they have understood that Spark is 100x faster than Hadoop. So say for an example, if a process is going to take, let's say, 100 seconds on a Hadoop system, right, it may probably just take 1 second for a Spark system to solve it. I'm saying it's more of a certain cases, not for every case, but usually 10 to 100x times better is Spark in terms of saving the space, saving the time compared to what a Hadoop is actually doing. Okay, so this is exactly what is called a Spark, guys. Okay, and talking more about Spark, in Spark we have lot of functions. Okay, one is like we have Spark context that we just spoke about, right? So he's going to take care of all the processes. Similarly, we have somebody called as Hive context. So he's a process who can control all the Hive tables, etc. You can read, write tables inside and outside Hive. Then you have MLlib. So this is a process which can help you do machine learning algorithms on top of this guy. We have Graphics. So Graphics will help you create graph related models. Okay, that's a beautiful thing that Graphics has got to offer. And all of these things, right, you can write it in different languages. You can write it in Java, you can write it in Scala, you can write it in Python, you can write it in R programming. So the Spark context, Hive context, your machine learning ML library, the GraphX library, all of these things are available in different languages, guys. You can make use of Java, you can make use of Scala, you can make use of Python, you can make use of R. All of these things are available in all the 4 APIs here. But very popularly, people have been using Scala and Python because they're very, very similar. Scala is like, 4 lines of Java code is equal to 1 line of Scala code. Okay, so Scala is much more faster, in fact, from what I've heard. Python is a little slower compared to other cases, but still Python is also very popular because right, most of the analysts or the data scientists today will be very proficient at Python, but not at Java or Scala. So they have an API for Python also, so you can go back and write a lot of PySpark codes on top of this guy. So please understand, guys, that Spark is more of a processing engine, okay? Like what we had in our previous cases, right? We had HDFS. HDFS is what? It's more like another storage, right? You have your plain hard disk in your system. HDFS is just occupying some amount of space of your hard disk. It's more of a process, right? So you can make use of the process to do all your analysis. Same thing, Hive. Hive is more about a tool, right? You went on to do a lot of analysis, right? Same thing. Spark is more of a tool over here. It's more of a a beautiful processing engine. You may start making use of this engine to do any of your processes here. You want to do plain analysis. You want to probably work on machine learning models. You want to work on graph models. You can do all those things using Spark as a processing engine. Okay. So this is everything about Spark, guys. It's not a very detailed introduction, but I think it pretty much covers 80% of the total. Okay, so what exactly is Spark actually doing? We have pretty much spoken about it. Now, as I told you all, in our case, right, for today's class, we are going to be combining both Spark and NLP together. We look at a lot of NLP related examples on top of Spark. Okay. So what you can do is, if you all have downloaded your Cloudera distribution in the last class, you can just go back and launch it. Okay, so this is our Cloudera distribution. I'm going on to launch this particular thing. So the machine has already got launched. Now you can just open your Spark shell by saying PySpark, and then you can hit enter. So you're opening terminal, guys, and you're just hitting PySpark. So what you can see is he's opening your PySpark engine right now. Okay, so you can see here. So he has opened our PySpark engine. He's saying that we are using Python 2.6.6 at the backend, while the Spark version that I'm working on is 1.5.0. So he's saying you may use Spark's processing engine to do all your processes. That's okay. But what Python code are you supposed to write? You're supposed to write a Python 2.6.6 code. Okay. So you can write this particular code and you can start making use of my Spark engine is exactly what he's telling us. Okay. So what we can do is, guys, we can go back and start writing a couple of Spark codes here. Okay. So we'll try to understand the transformations that we were talking about, right? So we spoke that there are general transformations and actions, right? So let's get introduced to all those things. So I want you all to notice this particular message here. What you can see is he's saying the Spark context is available as SC. The Hive context is available as SQL context. So what is he saying? He's saying the Spark context is available as SC. That is, the process is available as SC. Okay, it's given an alias. You just have to write this guy and start making use of the function. The other one is Hive context. It's available as SQL context. That is the name that he has given right now. What I will do is, guys, I'll open a new tab. I've actually brought in a small text file here as an input. Okay, so I have a small text file. I hope this is my text file. Yeah. So this is a text file we have here, guys, something called blog text. what we're going to do is we're going to make use of this particular text. Okay, this text data, we'll try to do things like, word tokenization, sentence tokenization, part of speech tagging. So we'll try to do all of these things on top of this particular guy right now. Okay, so we can go back and understand how do we use NLTK and Spark together. That is, how do you perform NLTK on top of, sorry, NLP on top of this Spark. That's exactly what we're going to be doing. So you can see that the file is available here. It's in your local. So local, your Spark cannot read it. It still needs to be part of your HDFS. So how can we push it? We can say HDFS. Just give me a second, guys. Okay. HDFS, DFS. Please put what? Put this particular file. So the directory of this particular guy is here. So he's at this particular path. We can go back and say, hey, this is the path. The file name is something called blogs text. So this is the file name I have. I want you to push it to, the HDFS, right? So I want them to push it to the HDFS. But before that, can we create a quick directory? Why don't we create a quick directory? So we can just go back and say HDFS DFS, mkdir. We'll create something called Spark. We'll hit enter. Let him create a directory now. Okay, HDFS DFS ls and give it a slash. You should be able to see that this folder would have got created, which is Spark, right? So you can see the Spark has got created. We just created it, right? So now what we will do is we'll say, hey, this particular file which is available in local, right? I don't think I can read it. Can we please push it into /Spark folder? Let's hit enter. If everything goes right, he should be pushing it there. Now we'll say HDFS DFS. Can you please let me know what are the different files available in the Spark folder? Let's hit enter. He is saying blogs text file is actually available on the inside. So everything looks cool for now. Okay. So what has happened? He's saying that yes, of course, the file is available on the inside. Now I think everything is pretty cool. So what we can do is, guys, we can go to Spark. Okay, so let's go to Spark. We can read the file and we can start doing a lot of operations on top of this guy here. Okay, so we're going to read the file first using the Spark processing engine. It's a text file, right? Luckily, so we can read the text file and we can go back and do a lot of transformations and actions on top of this particular guy right now. So let's do that. I'll hit Control L to clear the screen. So we can just go back and say, hey, data is equal to Spark context is available, right? SC. So SC dot, there's a function, something called text file, guys, where F is the caps, okay? There's a function called text file available. You just have to tell him what is the text file that he has to read. Basically, give him the name of the text file that is along with the location where it is. So you are saying is /Spark/blog text. This is exactly where the file is actually available. So you can just hit enter. If everything goes right, he should be able to read it. So he's saying what? Ensure free space called with this one. So it's basically clearing some space for us, right? And added broadcast, etc. So it's trying to read the file. Go back and say data and hit enter. He's saying what? Map partition RDD was created, right? So you wanted me to read the file, right? Since you're using Spark, he's saying map partitions RDD was created. I think there's this one RDD for now that he has created for us, right? What we can do is we can just go back and say data.collect. So collect is an action, guys, okay? So the collect that you see is more of an action. So shall I do something? I'll just create a small notepad. So vi spark.txt. Okay. Okay, so we can open the other text editor, which was gedit. Okay, so what we have done till now is, guys, we have read the text file and we have created an RDD, correct? A single RDD. So what we can do is we can discuss one action function which we call as collect. Okay, so the first guy is what? We have something called as collect. So the meaning of collect is like, suppose in case you have partitioned your RDD into several servers. That is, if you have created some partitions of your RDD, right? That is, if you have divided them into small pieces, it might be available in several servers, right? So when you say collect, what will happen is this guy will go back and collect all those RDDs for us now. Okay. So what is the action that we're doing right now? We are saying, hey, can you please go back and collect all the partitions for me right now? So can you see he's going back and collecting everything, which is actually one giant RDD for us. It starts from somewhere here. You can see, right? It's a list square bracket opening and it's closing over here. So it's a single RDD. So he has collected this particular RDD right now. So the first action that we have discussed is what? It's collect. So what is the collect actually doing? As the name says, he's just going back and collecting all the RDDs for us. This is function number one. Or there is also another action that you can do. The name is something called take. What is the name? The name is something called take here. Okay. What do you mean by a take? Take means, hey, can you please take that specific RDD only? How about only the second RDD for me? Or how about only the first RDD for me? You can specify which RDD you want him to take. Okay, so you can see that he's taking the first RDD. I mean, first RDD is not the right word, more of a partition, guys. Okay, so this is one RDD. Okay, but within that there might be a lot of partition. The take is actually taking a partition. So you're asking, hey, can you please take the first guy? Can you please give me that first partition alone? Or how about you tell him, how about the first 5? So versus you can say take the 5th one, or you can say give me the first 5th one. Okay, so data dot first, exactly one argument given. First takes a number, isn't it? Okay, first is only first, is it? I was expecting first 5. Okay. Or take 5, take means take 5 or take 5th. Okay, so he means 5, is it? Take 5. Okay, I'm sorry guys, so just opposite. Okay, so when you say first, right, it means the first guy, whereas when you say take, right, it means take these many people. So you're saying take only one partition, or take probably 2 partitions, take 3 partitions. So you're asking him to take as many partitions here. Okay, so these guys are basically going to go back and pull the result from the different executors available here. So one is what? One is collect. He's going to collect everything. Take will just go back and take as many partitions as you want. Then you have another function, something called first, who will pull out the first guy. And then if I'm not wrong, there is something called reduce also. We can talk about reduce later on. Okay. Even count is another action that we have. It can help you count how many times a particular thing is happening. We'll talk about count also. So the different actions available are these people. You have collect, you have take, you have first, you have reduce, you have count. So these are the different actions available here in your Spark, guys. So these are the actions. Similarly, you have lot of transformations. So I've been telling, right, that we're going to be doing a lot of actions and transformations, which your directed acyclic graph will understand, will know, it will keep a record. So the next thing is basically transformations. So when you talk about transformations, there are 2 kinds of transformations available. One is you have something called as a narrow transformation. Number 2 is you have something called as a wide transformation. So what do we have? Number one is we have a narrow transformation. Number two is we have something called as a wide transformation. So the difference between a narrow transformation and a wide transformation is very simple. So it's like this. So when you say, hey, this is one RDD, okay, or let's say one partition, whatever you call it as. So this is also another RDD or partition. Now say for an example, you apply a function. So you're saying, hey, can you please map a particular function for me on top of this people? That is, the data could be 2, 3, and 4. The function is the number should get multiplied by 2. So probably you're doing what? A map function, say for an example. So what will happen? You'll do a function on top of these RDDs, and the result of these RDDs or the partitions, you'll store it here, correct? This is what you give them an input, it goes through a function, it directly gets an output, right? So it's a pretty direct transformation that you're doing here. These kinds of transformations are called as narrow transformations. What are they? These kinds of transformations are called as narrow transformations. Whereas on the other hand, when you want to know what is the data available in the other partitions or the other RDDs. So say for an example, you're going to do a join operation. Okay. Whenever you do a join operation, right, you need the data coming from different people, isn't it? Right? So 3 different RDDs, I need to know what's happening in all the 3 people. I need to join the results coming from all the 3 people, correct? So these kinds of operations where it's not coming from a single RDD or something, but rather it's a result of many of these people are called as what? Are called as wide transformations here. So this one is a narrow transformation that we're able to see, while this is more of a wide transformation. Some examples of narrow transformations, guys, are nothing but there's one thing, something called map. We'll be discussing about it. There's another guy, somebody called as flat map. Then there is something called map partition. I'll see if we have any examples. I don't think so, but let's try. Then we have something called filter. Okay. Then we have a beautiful statistical function called sample. And then you have something called as union. I'm pretty sure there should be many, but this is what I remember. Map, flat map, map partition, filter, sample, union. All of these people are narrow transformations. Examples of wide transformations could be the join that you're going to do, or let's say the intersection that you're going to do. Or when you ask the distinct people, how many distinct values do you have? Or how about group by operations, right? Or group by key operations, reduce by key operations. So repartition, coalesce. So these are the different functions which qualify under your wide transformations here. So the first case is we have narrow transformations, while in the second case we have something called wide transformations. These are some examples of narrow transformations and some examples of wide transformations here. So what we can do is, guys, we'll go back and see all of these transformations in action. So let us go back to Spark. So we have spoken about narrow, we have spoken about wide. So whenever it comes to narrow transformations, some of the functions are, one is map, number 2 is flat map with M alone in caps. Then you have map partition where P is the caps, right? Then we have filter. Then we have sample function. I think we'll see sample function in action, in fact. Then you have union, right? Then when it comes to wide transformation, I think we will be discussing group by. We'll be discussing group by key. We'll be discussing reduce by key. This is another beautiful function. I think we might be even talking about intersection and joins. Let's see. Okay, we can also talk about distinct if you want. Okay, so these are the different wide transformations here, right? Map, flat map, map partition, filter, sample, union. Wide is basically group by key, reduce by key, intersection, join, distinct. So now what we can do is we can go back to Spark. The first operation that we did was we basically imported this entire text data, correct? Now what is the work to do? We may have to do what is called as word tokenization. Okay, now talking about NLP, guys. So in NLP, what are the different things that we usually do? One is you should basically import the data so that you can make use of the data, right? So step number one is you have to import the data. So we have imported using Spark right now. I'm pretty much sure you guys will know how to import it using plain Python also, right? Number two is we are going to be talking about an operation, something called tokenization. Okay, what is this operation? We're going to be talking about something called as tokenization here. So what exactly do you mean by tokenization? Very simple, guys. Tokenization is a process by which the large quantities of the text data that we are importing, right, probably as a text file or something, we are going to be converting into small parts, what is called as tokens. So what are we doing? We're saying that, hey, whenever I want to probably build certain natural language processing systems, right, or applications, I want to find some patterns, etc. at the backend, right? So for which it will be much more easier, rather than dealing it with a massive text data, we can bring it or break it down into small entities right now. So how can I break them into certain entities? We use a very popular process, what is called as tokenization. The different tokenizations we do are word tokenization and sentence tokenization. So what do we have? We have a word tokenization that you can do and a sentence tokenization that you can probably do. Okay. So what we should be doing is, guys, to do all this tokenization, etc., the word tokenization, sentence tokenization, etc., right? I want you all to install something called NLTK. So we need a library, something called as NLTK. I don't think I've installed it in Cloudera because it's a new setup almost. We'll check, we'll try to install it if possible. You should be installing something called NLTK. So you can just go ahead and say, hey, pip install NLTK. NLTK stands for Natural Language Toolkit, a very popular library here in Python. You call it as NLTK, Natural Language Toolkit. Once you've installed it, guys, the first thing I want you all to do is, I think we can probably try it in Cloudera here. Let's try it. Let's go to this one. Here we are. Okay, so we can just go back and say pip install NLTK. You can hit enter. It's going to give me an error, guys. It's not working since morning. I've checked it quite a lot of times. So you need to install NLTK by saying pip install NLTK. So I'll rather do it outside, okay, so that you all follow. So you can just go ahead and say pip install NLTK. Post doing that, you have to import NLTK, that is a natural language toolkit. And then what I want you all to do is, you need to download a lot of the functions as a one-time process. That is, a lot of the, let's say, models, predictive models available within NLTK, or the different corpus of data available at the back of the NLTK, etc., which is a one-time task by saying nltk.download. And you just hit Control Enter. It's going to open a small window for us right now. Or did you go ahead and download everything? I think that's what probably is happening. Usually this guy should open a small box for us, nltk.download, right? It should be opening a small box for you. Let me run it again. Let's check if it's opening it. Okay, it has opened it. Can you see it? So it should open a small box like this, guys. It's called NLTK downloader. So you can just go back and download, all the different things here. Actually, it's going to take quite some GBs and internets. I don't think you need everything probably. You can just install the first 3, that's enough. Okay. But in my case, I've actually done everything. So it'll just go back and save all the NLTK data over here. So the NLTK library is a pretty massive library. Okay, they have a lot of predictive models, etc. at the back end. So you can just leave it to the predictive models, etc. to do the work. So you have to download them by saying nltk.download, open and close parenthesis. It's going to open a box like this. You can just go back and say download, which will download everything for us. So this is the first step, guys. Basically, how you download your NLTK, or even before that, how do you install and download all the necessary stuffs inside NLTK. Now, what are we talking about? We are talking about tokenization, correct? So the way you can do tokenization here is two methods, as I told you all: a word tokenize, a sentence tokenize. How can you do a word tokenize? So you need to go back and import a function called word tokenization. Okay. So we will say from nltk.tokenize, I want you to import something called word tokenize, number one. Similarly, we can also say, how about something called sentence tokenize? Why is this not coming? CNT, right? Yeah. Okay. So we are saying, hey, I want you to go to this library nltk.tokenize, and I want you to import the two functions. One is word tokenize, the second one is sentence tokenize. Okay. And now you can just go back and hit Control Enter. He would have imported both the functions for you, provided you have downloaded everything. Okay. It will not work if you have not downloaded it. So you can just say from nltk.tokenize, please import these two people, word tokenize and sentence tokenize. Now what we will do is, guys, we'll create a small data. Okay, so the data is, let's say for an example, the data that we just had it here. I think I should have downloaded it somewhere here. It was called as what, block text something. Just give me a second, guys. Block text. Okay, so this is what we have, right? So what I'll probably do is I'll copy like 5-6 lines of the text here. I'll copy it. We'll go to Python. So we'll go back and say, hey, it's a single string of so much of data. Okay. So I can remove all these things also. Let's keep it a little lesser. I'll keep it more lesser. Okay. So you can see, guys. So we have created a string. Okay. So let's go back and hit Control Enter. Your data string has got created. So this is the data that you have. You have imported your string data. So using this giant text, right, you can't really do anything, right? You always need to start off by bringing or breaking them into small pieces. So what we can do is we can do these two operations, a word tokenizer and a sentence tokenizer. What are they going to do? Word tokenizer, as the name stands, is going to break it into small words. Sentence tokenizer, as the name says, is going to break it into small sentences. So we can go back and say, hey, I want you to tokenize for words out of this entire data. You can just go back and hit Control Enter. You can see that he's breaking into small words for us right now, correct? Similarly, you can import this function called sentence tokenize, open and close bracket, and pass the data over here. He'll be able to break them into single sentences. Can you see? He's saying this is a sentence. Can you imagine goes on as a sentence. It is difficult profession is a sentence. Here, this article is meant for big data as a sentence. The first case was word tokenizing, while in the second case, it is sentence tokenizing, right? So using plain Python, guys, we are not using Spark here in this example, right? So we are using plain Python and we are trying to do something called tokenization operation by importing NLTK and importing the two functions, word tokenize and sentence tokenize. Now, if you ask me a question, how would you do it using Spark? Not at all different, very similar, of course. Okay, let's go to Spark right now. if you had to use the same NLTK but on top of Spark, right? Once again, yes, you can do it. It's very, very simple. So we just have to go back and read this particular file as we did previously. So we've done it already, right? I think it's called data. It's not going to work, guys, in my case, this function, but I'll just kind of write it somewhere here. Okay, I'll write it here. It's not going to work, guys, because I don't have NLTK installed. I've tried my level best to install, but there are certain problems here. So we can just go back and say, hey, create a function, something called tokenization. We'll create a UDF. Okay, we'll create a UDF, something called tokenization, and we will just probably import NLTK even before that. Or let's say from NLTK, you can import your word tokenize and sentence tokenize, like what we did previously. Okay. Yeah. So now we can just go back and say, okay, give me one tab space. We can just go back and say that, okay, I'm going to receive some inputs like X, right? You can just take up this X. You can probably lower it down, bring everybody to a lower case probably to start off with, which we didn't do the previous case, right? So I can just say X is equal to X dot lower, right? And then we can probably ask him to return the result, which is word underscore tokenize of this particular X here. This is the function that we have, right? So we are saying, hey, let's create a UDF called tokenize who will take a single string and he'll go back and do word tokenization for us. Keep this aside, guys. Let me come back here. Let's come to Spark. Instead of doing word tokenization, if I were to write it, right? See here, definition, tokenization, X is the input I'm going to get. I want you to do X is equal to X dot lower. Okay, indentation block is problem. Okay, I'll write it here then. Okay, instead of using NLTK, I'll do it in plain case, guys. So we'll do X is equal to X dot lower. X is equal to X dot split it with spaces so that I'll get the individual words. Now we can just say, hey, go back and return this particular X. Okay, I hope this should be okay, provided it's 4 spaces. Okay, so let's go back and paste it here. Let's hit enter. The function has got created, right? The tokenization function has got created. What have we done already? We have already imported the data also called as data here. So now very simple, guys. If you were to do the same thing in Spark, right? Because it's a RDD, right? You always need to somehow make use of these transformations and actions only. You cannot apply the UDF as how you think. You should always be using only these transformations and actions. Which means going back here, I will say, okay, on the data, right? Can you please map a particular function for me? So you're saying what? Yeah, I've written a function, okay? What that function will do is he'll receive a particular input, he'll make it as lower and he'll split it with spaces and he'll create several words for me. That is a function. Now we are saying, hey, this is my data, okay? It's a RDD. The RDD might have got partitioned and distributed to the different areas. I don't know. Can you please map every RDD or every partition through this particular function? Okay, sure. What is the function name? The function name is tokenization. Now we can just hit enter. You can see that he is creating what? Probably 10 Python RDDs. Okay, so I'll go back and save it, guys. So I'll say data is equal to data.map. Let's look at data. He's creating probably 10 or 11 different RDDs here. Now we can just go back and say data.collect. I want you to collect all the results for me. Let's hit enter. Can you guys see that we were able to do the word tokenization that we spoke about? Right? Think, comma, off, comma, it, comma, for, comma, moment, comma, right? Billion, comma, imagine. Everything has basically got split into what? Single words, right? So what did we actually do? We said make everybody lower and split them using the space between them. That will create several words for me. Those words are exactly what I want. Now you can see this is the result. So instead of using this function that we wrote, that is the function who will do the word tokenizer, I've done it using plain Python, guys. But you can use this function also. You can just copy paste this function there and say this is the function that you have to map. Unfortunately, since we don't have NLTK installed, we can't do it, right? So this is the function I have written, but this is exactly what NLTK is doing. So you can use NLTK also. Instead of writing this function, you could have copy pasted this function and asked him to map this function on top of the RDDs also. Even that's totally cool. So here what we have done is we have written our function and we have asked him to do this particular mapping, that is mapping the RDDs to the a function that we've written. But we can see that for every sentence he is working separately, etc., something like that. It's all very nested. It's not looking very perfect. Hence we will flatten the result out by saying, hey, do not do the plain thing. So I'll go back and read the data again. Sorry. So yeah, now we'll say, hey, do not do the general mapping. Okay, I don't want you to do a plain mapping. Rather, can you do flat mapping? That is, after mapping and getting the result, I want you to flatten the result out. So we are saying what? After you work on top of the sentence by mapping the function, creating his words, right? Can you also flatten them out as a single data structure probably? Let's hit enter. Now let's go back and ask him to collect it and hit enter. Can you see, guys? It's become more of a single data structure right now, right? It's not nested like what you had in the previous case. Can you see? Everything was a list. But now everybody has got flat. They've become more of a single list right now. So the previous thing what you did was a plain map function, while now it's more of a flat map because he's flattening the result out. This is exactly what is the role of a flat map here. So same function. You could have just gone back and applied the tokenization function that you see here, even for a flat map. So the map is saying, hey, I apply a particular function on the RDDs, while flat map is saying, hey, post the map function, right? I also flatten the result out. So flattening is also something they do on top of it. That's exactly what is a flat map actually doing for us. So map is just applying the function on top of the RDDs here, while flat map is not just applying, but he's also flattening it out. That's exactly the work of a flat map here. So similarly, guys, let's look at an example of filter. Okay, then we can move on to the next topic in NLTK on top of that. We'll talk about this transformation also. So say for an example, map and flat map were doing what? They were applying a particular function on top of the input you gave, right? I'll do a filter. As the name says, or you might have already discussed this in your plain Python classes, right? Map, filter, reduce, etc. So now we'll do a filtering operation. So say for an example, I think I can relate it to NLP. Yes, I think I have an example to relate it with NLP. We can do that. Okay, so let's go back here. So one is you have tokenization. You have tokenized your data, right? So this one was using NLTK. How can you do a tokenization? Word tokenization, sentence tokenization. And how do you apply it in Spark? We have discussed that topic. So topic number one, post importing, how can you tokenize is done. Next thing is, very important thing is removal of something called stop words. What is the next thing? The next topic is basically removal of stop words. How can you remove stop words from this particular data? That is, I want you to filter the stop words, remove adjectives, etc. Right? Those people are all stop words. By any chance, can we just go back and remove all the stop words? The answer is yes, we can remove stop words. You can of course use your NLTK itself. So what you need to do is from nltk.corpus, if I'm not wrong, import stop words. No. Yeah, correct. It is imported. From NLTK dot corpus, you need to import something called stop words. So now if you ask him, hey, can you please let me know the list of stop words already available within the package? Let's hit Control Enter. Okay, it's not an iterable. Then how do we do it? It's usually an iterable, right? Or IN. Oh, it's a function. Sorry, guys. So stop words is a function. I need to open and close bracket if I'm not wrong. No. Okay. Okay, so how do we pull out the stop words? These are the stop words. There's a method of looking at it. Anyways, so what I can do is I can also visit to this path, which is much more easier. I think probably I'm not importing the right file. Let's check it. NLTK data. Corpora, right? It was Corpora stop words. Okay, I'm sorry, guys. We should have given the language. Okay. Stop words of English, I guess. Um, you can give the language somewhere. Okay. Okay, so let's try. So it's from stop words. Now it's dot English, is it? Dot English. I'm sorry, guys. I think I'll have to do a quick Google. It's been quite some time. Okay, dot words of English. Okay, that's a function. Okay, so there's a function called words on the inside. There you have to specify that it's English. Okay, so what you can see here is, guys, this is actually a already written list of stop words that is available within NLTK. Right, you can see that I, me, my, myself, we, are, ourselves, you, your, yourselves. So all of these things are the different stop words already available here within your NLTK library. So all we're going to do is, see here, we imported the data. We have done the word tokenization, right? So you imported the data, you did the word tokenization, right? Now we have imported the stop words also. We can say stops is equal to these people. Now you need to remove the stop words, right? So you can say, hey, my new data is nothing but I for I in data if it is not in the stop words here. That is, we are saying, hey, give me the word where the words are coming from this particular data. If it is not available in the stop words, if it is not probably part of the stop words here. Okay, so if not in is correct, right? If you don't need an in. Okay, so data I for I in data. So we can just okay. What happened? Okay, so this is giving you all the words right now, right? So now we just have to go back and say if not in stops. What is the problem here? Why is it a syntax error? So for loop followed by if condition, right? If else is here, if not in stops. So what is the syntax error here? Hmm. What's wrong here? Guys, do you see any mistakes here? If I not in, sorry, yes, if I not in stops, now it should work. Yes, I'm sorry, guys. So you should say if I is not in stops. I just wrote it as if not in stops. Okay. So what we are saying is, guys, let me just remove it. I'll start from first. We have taken up the data, we have tokenized it, we have imported the stop words. So the stop words are here, stops. Now we are saying, hey, the filtered data, I'll probably call it as filtered data is equal to I for I in data, which is give me each and every word, only if the word is not in the list of stop words I'm specifying. So say for an example, right? Our data had what? Let's hit control enter. The data had is for in everything here, right? Now let me do this. Let's hit control enter. Now let's open the filtered data. You'll not be able to see all of those. Can you see? Do you see a is anywhere? Do you see a us anywhere or are anywhere? It anywhere? You won't see it, right? You can see that all of this is gone. In fact, it's much more better if you had lowered this one. It works only with lower cases. So lower it, tokenize it, then import your stop words, go back and remove it. This becomes your final data. This is your filtered data. Can you see the in is not anymore, right? You don't see the in anywhere. So all of these things is basically what you're filtering it out. You're cleaning your data right now by filtering out the stop words. In the same fashion, you can also remove punctuations, guys. So what you can also do is you can remove punctuations. So if I'm not wrong, in the same library, there should be something called punctuations. No. Okay, let's ask for punctuations. In which folder is that guy in? Which area is he? Punctuations, punctuations, string dot. Okay, you can use that punctuation exactly. So we can go back and import from string, import punctuations. Yes, you can import this guy. Where the punctuations is nothing but the different punctuation marks. Even this is available here. So you can just go back and do the same thing again. So you can say, if this is probably not part of the punctuations, you can keep it here. Else you have to remove the punctuations is what we are saying. Now do you see? You know, punctuation marks may not be available. Those dots and all went away, right? I think a hyphen is available because it's probably not part of the list of punctuations. It's a big dash, I guess. Here it's a smaller dash, right? So most of the punctuations have also got removed here because they're not a word, right? So you can remove the punctuations also by doing this. So let's go start over again. One is we have lowered the text, we have imported the necessary people. Now we have filtered the data. You can see here exclamation mark, dot, slash, everything is available. Those are punctuations. Now we are removing the punctuations also. Let's hit control enter. This is the final data that we have got. So this is more like step number 2 that you're supposed to do. That is go back and filter your data. So what exactly are we doing? We are filtering our NLP data from stop words and punctuations here, right? So now if you guys ask me the same question, how we can do it using Spark. So using NLTK, how to do tokenization, we have spoken. And we did see some example. Using NLTK, how to discuss, how to do, the filtering of data, we have discussed. Now jumping into the version of it in Spark. So we can just go back and define the stop words, but unfortunately, since we don't have this one NLTK, we are not using that. Hence, we can go back and define it on our own. So we can just go back and say, hey, stop words are these people. I'll probably call it as is, am, I can keep it as lower I. Then we can just say are, the, let's say they, for, right? I can remove for, let's say how, why, where. So you can keep increasing a list of stop words, or otherwise you could have also imported your NLTK stop words. So I'm going to take up these stop words. I'll go back here and I can just say paste stopwords is equal to these people. Let's hit enter. So we already have the data, right? It's already done. So the data was already tokenized, etc. Right? Data.collect, you can see. We have already tokenized these people. So stopwords is here. Now we can go back and say the data is equal to data dot. We want to do a filtering operation. So previously is you did a map operation, right? You are mapping each and every object to the function right now. Now we want to do a filtering operation. Sure. Even for filtering, you have to pass a function for me. So he's saying you need to pass a function. Oh, is it? Sure. So we can just write a very simple lambda function, guys. I'm pretty sure you would have discussed in your Python class, right? We can write a lambda function. We can say, hey, you're going to receive an input X. I want you to keep X only if it is not in stop words. If X not in stop words or not in, I think not in. I don't think even if is required. X not in stop words. I think this should do it. So we can just go back and say, hey, lambda X colon X not in stop words. So this could be the function that we can apply. Let's go back to Spark here. We can paste the function, we can close it. Let's hit enter. You can see it has worked successfully. Now we can go back and ask him to collect the data. Can you see, guys, most of your stop words would have got removed? I mean, at least the stop words that we've defined, right? We define is, am, I, are, they, the, etc. You won't be able to see all those people. Shall we remove in and on also? Because we see that very often. So let's go back. So we'll say in and on also needs to get removed. Now let's apply the function right now. Let's go back and collect the data. So you won't be able to see in and on also right now. Do you see it anywhere? No, right? So this is the result of a filtering operation, which is another transformation that you can do in Spark here. So the first one was map, the second one was flat map, the third one is filter operation. So suitable examples using NLTK are what? You import your data, then you tokenize by doing a word tokenize or a sentence tokenize, and they're filtering out the stop words or the punctuations here. And here we can include the punctuations also. I can say, hey, remove a dot, remove a slash, remove a space, remove a dash, remove an exclamation. Go back and apply these people, then ask him to collect it so you can see. So these are a couple of transformations available in Spark, guys. So we have spoken about a couple of transformations, right? What are the different transformations? One is a map we know. Number two is filter map we know. Sorry, a flat map we know. Number three is the filtering operation, where this guy is working on top of the RDDs to produce, what I would say is filter RDDs. So the result of this one should be filter RDDs. It's saying Python RDD, but it's usually a filter RDDs here. So these are a couple of transformations available in Scala, and it's suitable example using NLTK. Or let's say, NLP examples. Okay. So any questions till here, guys? Are you all comfortable till here? Are you all able to follow what do we mean by Spark? What is exactly Spark doing? How is he different from Hadoop? And what do you mean by transformation action in Spark? What are the different transformations available? What are the different actions available? Comparing it with NLTK, how you do it in plain Python versus how will you do it in Spark? Are you all able to follow till here, guys? Any questions till here? Yeah. Convinced till here? How is Spark leverage for doing your day-to-day activities like NLP, machine learning, etc. Okay, perfect. Okay. So I think what we can do is, guys, we can probably take a quick 10 minutes break or 13 minutes break probably. Okay, so let's be back by 6:50. Okay. And then, we can just probably move on to the next few topics, okay, or the next few transformations and NLP things here, okay? So let's take a quick 12 to 13 minutes break, guys, and let's be back.
This conference will now be recorded.
Okay. Um, so what we have done right now is, we have been discussing about Spark and NLP together, correct? I don't see that there are any other examples where you can kind of, merge NLP and this one. I mean, when I mean by more and more, things like part of speech tagging, etc., we're going to be discussing more specifically for NLTK, but you can't achieve it those things using Spark perfectly, is what I'm saying. I mean, you need to write the functions and map it. So what we'll do is, guys, we'll discuss more cases on this one, the Spark piece, and then we can entirely jump into the NLP. Then we can, discuss on how it can be implemented in Spark, kind of go back and forth. So we've spoken about the map function. We understand the flat map. We understand filter function, correct? Then why don't we discuss about a function called group by? Okay, so we can talk about group by first. So the work of a group by, I'm pretty sure all of you would have understood already with the name. It's just going to kind of group all your words based on a particular thing. Let's say based on a particular entity here, right? So say for an example, if I would just go back here, so we had the data, right? We can just say, hey, I want you to group by, okay, group by what? Group by, let's say the name something like, let's say all, okay, we will check if there's something called all. So we can just say data is equal to data.group by. So anybody who's probably going to start with all, right? All those people will be grouped together. So we can just hit enter. Now I think we can just go back and collect everything. Let's hit enter. So there's nothing to collect. Oh, it's a string object. Okay. So we did data dot this one thing. Okay. So what we can do is we can write a list comprehension kind of a thing. So I can just go back and say, hey, print I for I in data dot. How about starting with take one? This is also not there because string is not callable. Okay. So let me start from first, guys. We had imported our data, which is this one. We went on to split it. Okay, tokenization function is here. We can do the tokenization. Then we can go back and do the filtering operation also. And let's just collect everything, or let's take one thing and we can check. So this is how it looks like. Okay. So now what are we supposed to do? Basically group by, right? I'll save it in a new object. So data one is equal to data dot group by. I can ask them to probably group it by, let's say something like all. All is probably not there. So en, we'll ask them to start with en. So is there any words which is all starting with en? Then data one dot collect. Let's hit enter. The string object is not callable. Okay. So how about data one dot take? Take is also not there. what just happened? It is supposed to work. So data is here, data 1 is here. Did these guys change something? I'm not very sure. Okay, I for I in data. Object is not iterable. Okay. Just give me 1 second, guys. Lambda of x. Okay, so I need to create a key value pair, right? So x 0 colon 3. How about this one? This might probably work. Huh. Okay. Um, okay. So let me tell you guys. So I'll tell you what exactly am I doing. Okay. So see here. So we have the data, correct? This is exactly what we had post tokenization and post filtering out the unwanted things, right? I mean, we were supposed to do a flat map. I think this is a result of a plain map. This is yet another problem. So reloading it again. Let's go back and do a flat map now on top of this guy. Okay, and then we can go back and do a filtering operation on also top of this guy. So this is where we stand currently. Okay, so this is the data we have. So data dot collect. This is exactly what we have, guys. Zoom in a little bit more. Okay, so now what we can do is we'll say data1 is equal to data dot group by. We're going to be writing a function again, guys. I think the mistake I made was not writing a function. So we can say that take up every input. Okay, that is like take up every group, I mean every word that you see, and I want you to find the 0 colon 3, that is the first 3 letters probably. Okay, it's like it cannot happen for a single letter, guys. That I think that's the mistake I was doing. So basically we are saying take up every letter, okay, and ask for the first 3 words if it's available, and let those be the different groups. So previously we gave a single group. Now we are saying there are different groups. The B is supposed to be a caps, okay. Now we can hit enter. Data1 dot collect. Actually speaking, they would have got grouped at the back end. Can you see? So he's saying LAS, it's one group. There are a lot of people on the inside. ITE is another group. There are a lot of people on the inside. EXE is another group where a lot of people are on the inside. Now we can just go back and say what I comma j. Okay, I can just say I comma j for I comma j in data of 1. That is, we are just splitting everything. Okay, so we are splitting each and every people here. So I comma j for I comma j in this one. So probably should I make it as a tuple here? Dot take of 1. I'll take one of the guy. Okay, so you can see here. Now he's saying, hey, this is one of the person, and this is basically the iterable you have. So the same code, we can just go back, the list, right? We can make it as an iterable. Now we'll tell you what are the different words. Can you see? Or let's say I'll say take 5. You can see, right? So he's saying here all is actually speaking a group with a lot of words like this. There is all, there is allocates, there is allows, there is few other versions of all. There is SCI is one group, there is science, and science. LI is another group, like is one group, here it's another group. So you can go back and ask for many cases, right? So he's saying here what? There's another group called SCA, scale is a word, scala is a word. So he was able to group all of these individual partitions or RDDs, whatever you call them as, or the data into different groups here, right? So it's just kind of creating what I would say is a key value pair kind of a thing, guys. Okay, so you have a key, you have a value where the values are nothing but the different groups you have. Okay, so we have exactly not created a key value pair, but of course, I mean, the answer is almost like this. So this is exactly what a group by operation is going to do. Similarly, there is a group by key. So group by is doing what? He's grouping all the values based on a particular key that you specify. Here it is group by key. That is, he's somebody who can work only on dictionaries. He can work only on dictionaries right now. So what we will do is we'll create a dictionary right now, okay? So I can just go back and say that on the original data, let us map each and every word and create a dictionary. I mean, not a dictionary, I'm sorry, but create a tuple like this where you just increment the count, okay? Every word followed by the number like 1. Let's hit enter. I mean, we need to save it somewhere. I'll call it as data 1. Let's hit enter. So when I ask for data 1 dot collect, right, he'll give me each and every word followed by the frequency saying it has occurred 1 time. It actually looks like a key value pair, isn't it? So this is a key, this is a value. This is a key, this is a value. It actually looks perfectly like a key value pair. Now what we can do is, on top of this key value pair, we can go back and say, hey, I want you to group it by the key, okay? Group it by the key right now. And we'll ask the result as it is. We'll just ask him to group it by the key right now. Let us save it in data. Okay. Now we can go back and ask for data.collect, you can see. So he would have, grouped the different people right now. So this is one group. So there was a key something called write, I've grouped all of those people. There was a key something called check, I've grouped all those people. Again is a group, I've grouped all of these people here. Right? Now you can go back and write the dictionary, something like this, what we wrote previously. Hit enter, can you see? He's saying increase is one group, there were 3 words or 3 repetitions. Manager is one group, there was 1 repetition of it. Partitions is one group, it had 1 repetition of the same thing, right? So same thing, guys. Previously you did a group, right? It was just grouping based on a particular value, but right now it's grouping based on a key. So that was a group operation, well, this is a group by key operation, right? So that was a plain group operation, guys, but now this is a group by key operation here. So now what we can do is, we can probably apply some functions and we can find the frequencies in fact. So data of 1 is what? Is a result of a group by key operation, right? So we can just say, hey, can you please map all the values to a function like sum? So we're saying what? Hey, can you please map all the values to a function like sum? I'll store it in data of 2. Let's hit enter. Now go back and say data of 2 dot collect. So he's saying int object is not iterable. So, okay. Instead of collect, how about take of 1? I think it should be the same result. Now is where he's actually executing it, okay? Previously, you would have just compiled it. Now only he's executing it. Okay. So dot map values dot, I'll create a dictionary probably. Dot map lambda of x. We'll create a dictionary like this. We'll say x of 0 comma x of 1. That is, I want the key and the value right now. So this should do it probably. Okay, let's hit enter. So data2 dot collect, and now we can hit enter. Still there is an error, int object is not iterable. Okay, so data1 dot collect. So we had all of these cases, guys. It's basically a key value pair kind of a combination, correct? This is basically the group that we have created, correct? So now what we need to do is, we need to go back and apply map values on top of this one. So that's what we did. So data1 dot map all the values to a function like sum. So we are saying map all the values to a function like sum. You can just hit enter, right? I can probably try to take one of them. Why is it saying int object is not writeable? Okay, so map lambda of x to x of 1 and x of 0 like this dot sort by key. Is this working? Int object is not iterable. Okay, data1 dot collect. This is where we were, right? What's going wrong? What's going wrong? What's going wrong? Data1 dot collect. So this is the original frequency we had, correct? Sorry, it's still not grouped, right? So data2 is equal to data1 dot group by key. Let's hit enter. So data2 will be the grouped RDD, actually speaking. Now on to top of this guy, we need to say map all the values to a sum function. Now we can probably try to take one out. Sorry guys, there was a mistake in the names. So let's go again. See here. So let's first import the data. We will start from there. We'll import the data. Importing the data. Flat map. Next. Flat map. Then filter. Okay. Filtering it out. Then what are we doing? We are going to basically take a look at it. So this is where we are. We have all the words. We are trying to find the frequency of this one. So we can just go back and say, data1 is equal to data dot group by, or even before group by, I think we need to create the this thing, key value pair kind of a thing. So we can just go back and say, hey, I want you to map each and every word that you have here into a tuple which will have a number 1. So data1 dot collect, if you do it right, every word will have a 1 at the front. So now we can say data2 is equal to data1 dot group by key. Now we are saying group it by the key. So the keys could be these people. So here is a key, R is a key, random forest regressor is a key. They are the keys, he'll group them. So data2 dot collect, if you check, the keys should be available followed by the iterator. So you can say I comma list of j for I comma j in, sorry guys, it was data2, right? If I'm not wrong, in data2. Data2, isn't it? When you did a dot collect. Okay, so data2. So now what we can do is we can just go back and say I for I in data2, I want I of 0 and I want list of I of 1. We have to do it like this. Hit enter. So I need to convert this as a tuple. Dot take file. Okay, so you can see each and every word he's counting how many times has it come. I mean the different ones and all he is actually grouped right now. So data2 dot collect is having the key value pair combinations like this, correct? So now we can just go back and say on top of this one, map all the values to a sum function. So we're saying what? Map all the values to a sum function. So now you can also ask him to collect it. When you hit enter, you can see he's actually applied a function on the values part of it. So map values, as the name says, what? He's mapping all the values available for every key to a function. The function is namely sum here. So you're finding the frequency. So he's telling you start has occurred 8 times, Java has occurred 2 times, or SQL context has occurred 4 times here. So it's letting you know what is the frequencies here, guys. Right? So what are the different functions that we just discussed? We have a group function, which is doing a plain group. You're just saying, hey, each and every word, right? I want you to just group them. But group by key will work on a dictionary format only. There needs to be a key value pair combination. It can't work on plain values only. It needs to be a key value pair kind of a tuple. Then you're asking him to group it based on that key there. Then I think map values, right? We don't have it here, but map values, I'm sorry guys. So map values is also speaking another function, which was mapping a function to all the values in a dictionary. Right? That is also a beautiful function, something called map values, right? Reduce by key is actually speaking going to do the same thing, guys. In fact, speaking, so reduce by key is like he's going to search for a particular key and you can ask him to do a particular operation. Okay. So say for an example, if we had actually stored this result somewhere, data 3 is equal to this one. So we'll store it somewhere. So we can just say, hey, data 3, I wanted to reduce by the key. That is, for a particular key, I want you to do something. So he will receive both X and Y. You can probably ask him to do X plus Y, but I'm pretty sure it might not work. Or let's create a tuple, X comma Y again. Okay, now you can just hit enter. Data 3 is a list here, is it? Okay. Data 2. Yeah. So now you can just take 5 and check it. Now you can see. Okay, so reduce by key is the same thing, guys. Map values was doing was it was working only on the values part, right? But reduce by key is like, okay, search for a particular key and then on top of it, let's go back and do some work. So this is the same function you would have already learned in your Python classes, right? The reduce function, the same thing. Now you're reducing it based on the key right now. So we have a map function, we have a flat map, we have spoken about filter, we have spoken about group by, we have spoken about group by key. We know what is a map values doing, we know what is a reduce by key also doing. So these are the different methods, or let's say transformations that is available here in Spark. Right? So these are the different transformations. Reduce by key is doing what? He's searching for a key and he will start reducing them. Reducing based on what will be the function you pass. Okay. So the next few things are very easy, guys. The next functions are all totally easy. We can just go back and create a, RDD probably like this. So we will say, let's talk about probably data of 1 dot collect. Okay, so now we can just say, hey, data of 1, right? This guy is there. I want you to sample with replacement, without replacement. So we can say, hey, without replacement. So how many people? How much is the fraction that you want? So we can just go back and say that, I probably want 20% of the data set. Okay, is there any seed value you want to keep? Okay, you can take a seed value of 100, right? So I can just store this data and let's say data 4. Now data 4 dot collect, if you do, he will print all the sampled ones. So this is what? This is going to be 20% of the total. So I can ask length of data 4 dot collect, and we can also ask him to give the length of data 1 dot collect. So I'll write it in a print function so you can see. So 4797 is what we had originally, times 0.2 is what, 930, right? Or whatever it is. 20% is what we gave, isn't it, as an input previously? You can see here. So we are asking 20% of it, which is 930 or something. right? So that is exactly what a sample is going to do. It's going to sample records, as the name says, right? Next is union operations and all. Union is also simple. So previously we have taken one sample, right? Okay, anyways, I'll do it from scratch. Okay, so data of 4 is equal to data 1 dot sample without replacement 20% with a seed of 100. Data of 5 is equal to same thing, another sample seed of, let's say, 10. Now you can just go back and say, hey, I want the data 4 to be probably unioned with data of 5. So you can ask them to get unioned. It's going to give you a union, RDD. Then you can ask them to probably collect it also. I'm not very sure if I should add a bracket here and ask for a collect. Right, so he's going to collect all these people. Similarly, you can go back and ask him to also join. You can ask them to get joined here. So join is also another transformation that you will do. Similarly, you can ask for the distinct people. So you can say, okay, from data 1 that we have, right? So you can just ask for the distinct entries. So what are the different distinct values we have for now? So it can give you all the distinct entries here. So this is another function we have, right? So all the distinct values are available here. So we know what's the union doing, what's an intersection, what's the distinct doing, right? I think this should do it. This should be the different functions here, right? So map, flat map, map partition. I'm not very sure what it does, but I just remember the name. We know what's a filter doing. We know what's a sample doing, right? So you're just going to tell whether sampling with replacement or not, how much fraction should he do it, how much of seed are you giving, so he can sample values for us. Union, as you may do, it's going to do a union operation, group by key, everything is okay. Intersection, right, it's another function, you'll know, you can just change it to intersection. Finally, this is a join function, and finally this is a distinct function, so it's going to find the distinct numbers here. I think these are all self-explanatory, right? So these are the different operations or the different transformations and actions you do in Spark, guys. But this is like, I would say 80% is a Spark. Any operation you want to do, somehow you have to achieve with these people only. If you don't do it, you can't produce RDD, which means you can't work on Spark, else you'll be working only on plain Python. So you need to use all of these transformations and actions somehow. Only then it means you're actually working on the RDDs, or you're actually working on Spark. Else it means you're just working on, like plain Python or something. So that is very, very important. So I think with this, we are kind of done with Spark. In fact, apart from that, I think there are statistical functions like count and all. Okay, so say for an example, in any case where we have a count, I'm not very sure if count and all will work here, but we can try it. So you can ask him to count something, it will not work because it's a pipeline RDD. Right. On top of this guy, it might probably work. No, okay, name. Int object has no attribute count. So these are certain other functions, guys. If it's like pure numbers and pure values only, right? You can do count. I think somewhere over here there is a number in this list here, right? There is a number. That's why you're not able to count. So count will help you count people. And if there's only numbers, right, you can use functions like min, sum, max. You can use standard deviation. There's also another function, stdev only. Standard deviation. Variance is another function. So count will work if it's only string values. All of these functions will work if it's only numerical values. So you can find the count of particular values, right? You can find the min, max, variance, standard deviation of the numbers. So all of these are mathematical, statistical actions. They are actions, if I'm not wrong. They are not transformations, they are actions because they are aggregating some results, right? So these guys are all actions. So count is there. Then you have min, max, sum, variance, standard deviation. So these guys are also actions because they don't transform anything really. They're just aggregating the data, right? They're just aggregating the outputs. So that's why they fall under this one, something called as actions. I think that's it, guys. With this, we are kind of done with Spark, right? So other things will be just by using Hive context. You can play with your Hive and all. Okay, so I think it's pretty simple. I think with this, we are done with Spark. What we can probably do is we can just jump into more and more of NLP. Okay, so we can just quickly discuss a couple of more NLP things. So how about, let's say, something called part of speech tagging. So in NLP, we have POS. Okay, POS basically stands for part of speech tagging, a very popular operation that we typically do. So what happens is, guys, so whenever you get a text data, right, after doing tokenization, removing stop words, etc., some people might want to understand in which part of the speech was this particular word there, or what was the real meaning. Do you think it was more of an adjective, or was it probably more like a modal, or was it a noun? Was it a proper noun? Was it an adverb? So what was the kind of grammar that these guys were using? Okay, you can call it like that also. They want to understand what is the intention of the word in that particular area of the speech. That's called part of speech. So to do it in NLTK, guys, in plain Python, you can just say from NLTK, let's import part of speech tag. So let's say, for an example, we give a string. Okay, I'll assume some string here. So IP input is equal to hello, my name is Robert. Let's say I am coming from, let's say, England. I eat, let's say, bread. Okay, so let's hit control enter. So this is a string we have. So what you need to do is, guys, you need to take up this particular string and just pass it to the parts of speech tag function. So we'll just say POS underscore tag. Why? Because he himself is going to tokenize the words and he can give you what was the the meaning of this particular word. So we'll pass the input. Let's hit control enter. Okay. Okay, so he has done a letter tokenizer. Then I think we need to tokenize it then. I'm sorry, guys. So word underscore tokenize and pass this by. Now it should be correct. Okay. So what is this guy saying? He is saying this hello is a word. It was part of your speech here, and I'm giving it a tag, something called NNP. NNP basically means it's a proper noun. Okay, so NNP here basically means it's a proper noun. Okay, I'm not very sure if it's right, but do let me know if it's wrong. He's saying hello as a word is probably a proper noun. And then for my, he's saying PRP, right? PRP is actually personal pronoun. PRP is what? PRP is personal pronoun. Okay. Similarly, NN should be just singular noun. Okay, name NN is basically saying it's a singular noun. Then examples, VBZ, right? What is VBZ? It's verb, if I'm not wrong. Verb. Then NNP, IN. IN, is that right? Yeah. IN. This IN is actually speaking a preposition. Okay. So all he's doing is, guys, he's just taking up the different words that we had in this particular string and he's trying to find what do you probably guesses is the meaning of all of these words, or what was the speech, or let's say what was the intention of that particular word there? Was it a verb? Was it an adverb? Was it a noun, proper noun, common noun? Right. So that is exactly what this guy is actually going to help us understand. Right. So depending upon the area or the way of usage, a particular word will work in different fashions, right? So that's what he's actually doing. So using a parts of speech tag, you can understand, what kind of a word is it? Was it a noun? Was it a verb? Was it an adjective? Whatever it is. So you can understand what is the grammar behind it. What is the part of speech for this particular word here? That's another thing that people do. Okay. Next is, I think we'll just close with this last topic. It's once again another filtering operation, guys. What we call as stemming and lemmatization. Okay. So we have something called stemming and lemmatization here. So what exactly do we mean by stemming and lemmatization? Simple. It is actually another technique of normalizing your data. That is, the first case, what we did was we went on to remove all the stop words, etc. Right? Now this is another technique of going back and normalizing your data. So when I mean by normalizing, so say for an example, somebody might use a word like riding. They might say ride. I don't see any other, or let's say eat. Somebody might say eating. You might see Uber Eats. This is another fashion. Somebody might say eat. Somebody might probably use the word ate. So it's more or less kind of the same thing, but in different areas it might have different what I would say is usage, right? Or different kinds of morphology, whatever you call it as, right? So what we're trying to do here is, guys, we're trying to make people understand that, okay, by the end of the day, I think all the four people are same. Here it's more of a, in a progressive state, ing, but here it's more like eat or ate is all past tense, etc. But ultimately they all mean the same. So we want to normalize all this data. Hence, for normalization, there are two popular operations we do. One is stemming, number two is lemmatization. So in a stemming, guys, what it will do is it will basically kind of break the word. That is, it's going to cut the word and remove the last piece of it. That's it. You can see here from nltk.stem import Porter stemmer. This is one of the model on the inside. It's called Porter stemmer. So say for an example, if this is the input we are going to give, input is equal to a list of these people. It has to be a string, by the way. Okay. Now we can just go back and say my model is equal to a Porter stemmer. Let's hit Control Enter. And now we can just go back and say, hey, for I in this particular words that we have, which is input, I want you to print the result of pushing this particular word inside the model right now. Okay, I think I'm making a mistake. It's actually model dot stem. I think there's a function called stem. Correct. I need to pass it to the function called stem. So here it's more like a model. Now we're going to fetch one word, guys, and we're going to stem it. So let's hit Control Enter. You can see what's happening. Eating, you have cut it. The ing has got cut and it became eat. Eats, the s was cut. It became eat. In eat, it is as it is. Ate, there is nothing to cut, so it is available here. So eating, eats, eat, ate, it is all kind of what? It's working on top of this guy. It's doing a simple slice on this particular guy and he's able to give you the rest of the piece. Now, what do you say? All these three words are actually meaning the same. Eating, eats, eat. They're all the same. Ate is more of a past tense. So stemmer is just trying to cut something, but there's nothing more to cut from this guy. So he just leaves it. So this is the work of a stemmer here, right? So what is the stemmer doing? The stemmer is just kind of, working on top of the words and he's cutting them off. Right? It's just working on a slice and it'll remove either the first piece or the last piece over here. That's exactly what a stemmer is doing. But a lemmatization is a little different. Compared to the stemmer who's removing the suffix or the prefix, right? This guy is going to go back and understand the lemma, or he's doing what is called as a morphological analysis here. Right? So he will do a, kind of a very in-depth analysis, and he will understand what do you probably think is probably the, kind of a lemma, or I think all of these words could be in the different forms of those lemma. Can we just go back and find what will be the original lemma or more of the root word? That's called as lemmatization. So let's probably look at an example of lemmatization. So we will say from nltk.stem import WordNet lemmatizer. So this is a model available on the inside. Once again, you can say model is equal to WordNet lemmatizer. You can hit from Control Enter. Now I'll copy paste the same thing here. Instead of stem, I think stem is still good, or lemmatize. I think it's called lemmatize. Okay. So now what we're going to do is we're going to say, hey, model is a WordNet lemmatizer. This is your input. Now I want you to apply a lemmatize function here. Now let's go back and hit Control Enter. It's working on each and every word. Okay, this is surprising. Eating as it is. Okay. Model.lemmatize a y. Studies, let's say, study. There should be enough. Let's try this one. Okay. This is a little surprising. Why it's not working? Dot lemmatize of WI. Okay, this seems to work. What was the problem in the previous case then? Study, studies, studying. Okay, I'll go back and comment this guy out and this guy out. Okay, for studies it's working. Studying ing should get cut out, right? No. Okay, so progressives, or leave it as it is, I guess. I'm not very sure. I'm not very sure what happens inside the lemmatizer, guys, because it's a predictive model that these guys have created. Okay, it's going to work a little differently. So I think this example was a good one, right? Where we kept it as cries, cry, and crying. When you go back and hit Control Enter, everything by the end of the day has become cry. So cries has become cry has become cry, crying ing has also become cry. I don't know why for studying, etc. it was not working, but ideally it should have done it. But anyways, so in this particular case, you can see, right, compared to the previous one, where if you had probably used a portable stemmer. So let's compare the result from a stemmer. Okay. So this would have been the result from a stemmer. It's all CRI, CRI, CRI. What does CRI actually mean? It doesn't mean anything, right? But when you do a lemmatization, it's cry, CRY. So CRY, cry makes much more better sense here, right? So this operation is exactly what is called as lemmatization, guys. It's a little bit more costlier in terms of computation type, but in terms of working better, I think lemmatization is far, far better. So, probably you don't want to use a stemmer, rather you may want to start using lemmatization operations here. Okay. I think these are the different things that you have to understand under NLP, guys. But today in NLP, some things have got a little bit more advanced. Things like there are word embedding models that people have created that's more related to very advanced neural networks. Then sequence to sequence kind of a models like the RNN that we would have spoken about, right? So sequence to sequence kind of model using deep learning. I think this at least we have discussed, but we saw a time series case. So these are the little advanced stuffs that has come under NLP, but I'm pretty much sure that the other things are all, plain regular expressions and the plain things what we were discussing till now. Some tagging problems, that is POS has certain tagging problems. It's not very accurate. So some people will go back and create something called hidden Markov model. That's another improvement that you see today. Okay. I think this should do it, guys. So these are the different NLP stuffs. The last three things we are not discussing because it's a little out of scope for us. So people today are creating hidden Markov models or word embedding models or sequence to sequence models. So you can probably, look into these things, but otherwise, the general NLP that you always require when you want to work on NLP data or text data, I think we've discussed all of those. Okay. So we have spoken about Spark as a processing engine. We spoke about the actions and transformations available in Spark. So we try to compare how plain Python is doing the job and how you can achieve the same thing in Spark also, right? So all these codes that you write, right, you can just convert it as a function and you can just go back and write it as dot map. Like how we were doing, you just say dot map this function, dot map that function. The same thing, guys. You can write the same NLTK code and ask your Spark also to do the same computation. Because by the end of the day, Spark is more of a computation engine. You start making use of Spark, his technologies like RDDs, etc. the moment you start making use of these actions and transformations. Else, if you do it, it's like plain Python only. It's like you're doing plain Python. So the plain Python functions, you're going to use it on top of RDDs by using the RDD related transformations and actions. That's exactly what you need to understand. Okay. And under NLTK, we have spoken about what? Starting off with this tokenization, word tokenization, sentence tokenization. Even before that, we spoke about how to download and install them. Parts of speech tagging, we have done that. Normalizing data using stemming and lemmatization, stop word and punctuation removal. So these are the fundamentals that you need to understand in NLP, natural language processing. Okay. So there are more libraries, guys, that you might want to probably go back and explore. NLTK is pretty powerful. Most of the things are covered here. Natural Language Toolkit. Okay. Apart from that, you can also try spaCy. Okay. So spaCy is also another beautiful, library available here in Python. So you can even try spaCy. spaCy is also pretty nice. So what a spaCy and all can do is, it can have better models. It's having better models. It can go back and tag your words, etc., in a much more better fashion. In fact, there is something called what's the name of it? What do we call a named entity recognition? So there's a beautiful concept, something called named entity recognition. So here, whenever you write, let's say a tree, a car, let's say a bike, this guy will, or let's say a mango, this guy might probably go back and say that, these are all nouns, probably, let's say common nouns, right? But a named entity recognition, NER, is a little bit more in detail. So he will say, hey, car and bike, these are all vehicles. It's another level further. He can say that tree is more, let's say, something related to forest, or he can say mango is more related to fruit. That is called named entity recognition. It's one level further. In fact, it is there in NLTK, but is not very powerful. Only in spaCy library we use named entity recognition. So you can see NER. It's very powerful. The spaCy library's NER is very, very powerful. So this is one example somebody has given, I guess. Okay, can you see? 5.1 billion comes under money. Google is an organization, right? Wednesday is a date, right? So this is something that he has done with NLTK, I guess, but the next one should be probably with Spacey, if I'm not wrong. Or this is still with NLTK, right? So it can tell you different things. I'm pretty sure this is from Spacey. I saw happy somewhere. I think should be this one. This all should be from Spacey, if I'm not wrong. So it's saying person, GPE, right? What else? So they can help you name what the words are actually. That is what is called as named entity recognition. Can you see here? He's saying Google is an organization, Wednesday is a date, etc. So this is called as named entity recognition, guys. This is also available in NLTK, and it's also part of Spacey, but people typically use Spacey because that's much more powerful. Okay, that's another beautiful library. You can probably have a look at it. Okay. Yeah, so I think with this, we are probably done for the day, guys. So that's the amount of Spark that we need to kind of understand. What are the transformations and actions? And here we have spoken about the different NLP things also. Okay. So any questions still here, guys? Are you all okay? I understand that it was a little fast, but yeah, because Spark is something, it's a little too much. We don't have to really deep dive here. That this is everything that we need to understand about Spark. And NLP also, it's like pretty simple topics. So these are different functions in NLP. Okay, so that's why I was a little fast with the assumption that you've already gone through your Python classes. Yeah, so any questions for you guys? Can we call it a day? So the last weekend's recording, yeah, I forgot the Yatinder. I'll probably do it now. Okay, including this one. I'll try to do it by late evening today. I'll surely do that. Sorry, vectors in NLTK. What is vectors? So you think I'm coming across? Oh, you mean to say word to vectors? Word to vectors, this one? Okay. Yeah, so this is a word to vector model. It's a general model, okay? So anybody can create. In fact, you can create your own word to vec model using a multi-layer perceptron here. Okay. So using a simple MLP, you can also create a multi-layer perceptron. So it's called word embeddings here. So basically the concept is like, instead of having them as words, right, rather can we convert them as numbers, something like vectors, so that you can understand how similar are the words or how far are the words, etc. That is what is called as word to vector. That is, the words which are all basically strings, right? You will convert them as numbers. You'll basically convert them as vectors. So a word to vec model will look like this. Can you see? So this is how it will look like. So each and every word will get projected in a axis like this. So these are all having different values. For different features, it'll have different values. Now you can go back and compare the similarity between the words or the dissimilarity between the words by using vector algebra. So that's called as a word to vector models. So it's actually, yes, it's available within NLTK. You can see here. So in NLTK, there is a word to vector model that they're using. Then they are converting all the words to the vectors. Then they are starting to find, what is similarity between them, etc. I'll just quickly refresh it so you can see here. They're finding how similar are they, how dissimilar are they, etc., etc. You can create your own word to vector models also. That is, you can create your own embedding models also. Okay, so that is the topic that I told you right here. So the word to vector or the word embedding models. So we can go back and create it, or you may use pre-built models also here. So it all depends on us. Okay. Okay, so any good book for ML or any good soft copies I can share you on. I'm pretty sure Shrikant sir would have told you about this one, right? So, what's this guy's name? Machine Learning with R. The author is, what is his name? Machine Learning with R by Brett Lance. Correct. I'm pretty sure this is a book that Shrikant sir would have told you, right? Else I'll just give you all the link here. So Brett Lance, this is a very good book to start off with, at least to start off with. So the first level of understanding you'll be getting when you read this particular book. I mean, the examples are too simple, okay? It's like using iris data, what would you do, etc., etc. But it's a very good start, actually speaking. So he'll tell you how regression models will work. How do you implement an R? How do you implement an, implement, let's say, neural network in R, etc. This is very good conceptually, and also understanding R. This is good. Machine learning wise, it's very good. Any other books? Mostly, what I do is I have separate articles as such. So I read university articles and all. Example, if it is SVM, right? For SVM, there is this guy called Andrew Ng, right? So he will give you a very good PDF here. It's a very good article. You read this, it means you've understood entire SVM. So you can just go through all of these lecture notes. So you can take up different universities, lecture notes, etc., and this should be good enough. So don't follow one strict book. Rather, for every model, go back and try to fetch the different lecture notes here. So different people would give you different lectures, etc. Similarly, for random forest, there's another guy. I forgot his name. So what I will try to do is I'll try to upload some books that I have with me, that is independent articles like this. I'll try to upload them. I'll create a separate folder and do it. But as a general input, I'm just saying, so don't stick to a particular book. Go back and try to fetch individual lecture notes for each and every model that we have discussed here. That'll be far, far better. Similarly, for linear logistic regression and all, there's a book on CFA. I'll probably upload that one. CFA level 1 book is there, so that's actually pretty good. It has pretty comprehensive stuff. I'll probably upload that also. Okay, so any PDF that I have, I'll probably just upload. You guys just have a look at it. Okay, so I think then we can call it a day, guys. So tomorrow's class will be handled by Shrikant sir. So he'll be taking you through Power BI, because um, I'm very new to Power BI, so it's better that I leave it to an expert. Okay, so Shrikant sir will be handling Power BI and Power Query, I guess, for tomorrow. Okay, yeah. So thank you guys. Thanks for joining. Okay, so let's catch up another time. I think probably tomorrow might be our last class. I'm not very sure. Still depends upon Shrikant sir. If he wants to just extend it for next week also, he'll let you know, guys. So thank you guys. Thanks for joining. So let's meet another time. Oh, sure, Yatendra. Thank you. I should say thanks to you.